the log tables are such an asset that you really need to be able to use them properly. They tell you so much information to do with, you know, your differentiation. And in this video, I'm going to just kind of run through a lot of this side here, the left side, because if something looks exactly like what's on the left here, then we automatically can look over here and see the rule of what we do in order to find the differentiation of it. But, you know, like I said, you need to understand what your log tables are saying. So your x is your variable. So, I mean, obviously it doesn't have to be x, but that is the variable. N is a number, like, you know, x to the power 3. So x cubed. So in the last video I might have looked at, right, if you want differentiation x cubed, you bring the power down in front and you subtract 1 from the original power. So I end up with 3x squared. But that might be the most common one, but that doesn't mean it's the only one that we use here on this side of the page. You know, so we have ln x. Now ln x is log in the base e, and I'm going to look at that in a few minutes. And the differentiation of that is just 1 over whatever the variable is. But it, you know, it has to be ln x. We won't use this if the function is ln 2x, because it doesn't look like what's here. What is here is ln of a variable, not ln of 2 times a variable or ln of a variable squared. If it doesn't look like this, we'll have to go to this side of the page. But if it does look exactly like this, it's very straightforward. You know, if I have f of x is equal to ln x, then the differentiation of it is 1 over x. E to the x. So we know the number e, you know, it's in your calculator and everything. It is a number, so there's not a variable here, and it's to the power of a variable. So e to the power of some variable, so e to the power of x. And actually, strangely, but when you differentiate it, the differentiation is actually the same. That's kind of unusual, but you know, we can have a look at that. What does this mean? So let's say, so a, you know, turns up here a bit, has to be a number. So like e to the power of 2x, e to the power of 3x. That means that if you want the differentiation of that, so let's say we did e to the power of 2x, that's, you know, we have the e, the number is a 2, so the a is a 2, and then we have our variable x, which means the differentiation of it is 2e to the 2x. Again, a is a number, so maybe 5 to the power of x, or 7 to the power of x, or 2 to the power of x. The differentiation of it will be that. Cos of x, the differentiation of it is minus sine. Now, if you saw cos of 3x, you do not use this side of the page. We'd have to go to this side of the page because it looks different. Or if you saw cos of x squared, no, that's not what's here. So we'd have to, you know, do something about that. We'd have to look at another option because it has to be cos of a variable. And if you differentiate that, oh, it's minus sine of that variable. Tan of x, or tan of a variable, okay, so that's sec squared of the variable. Inverse cos of the variable over a number, so let's just say inverse cos of x over 3. You differentiate that and it tells you, well, it's minus 1 all over the square root of 3 squared minus x squared, if the a here was a 3. Again, you know, if you saw inverse sine of 5x over 2, no, we don't use this because it has to be just inverse sine of a variable over a number. So if we saw inverse sine of x squared over 3, again, it doesn't look exactly like what's in the log table, so we're going to go to this side of the page and see what we can do. And tan inverse would be this. And again, a has to be a number. So now I'm going to look at what this means again, because, you know, we looked at differentiation from first principles. You want to be able to understand that it's about the rate at which the function is changing. But what does that really mean? So I want to have a look at even just, let's say this function here, we look at sine x. There's your graph. What is the rate at which the graph is changing? Or another way of asking that is, what is the slope? But sure, it just depends. Like, do you want the slope when x is minus 180? Because that looks like a bit of a minus slope there. Do you want the slope maybe here somewhere? you know, it still looks like a minus, but it wouldn't be as steep as what's here. Do you want the slope here at minus 90? Because that looks like it's a 0. Do you want the slope here, here, here? Like, where do you want the slope? So if we go to our log tables and we have sine of x, well, look, that's here. That's exactly here. So if you differentiate sine x, you get cos x. What have you just found out? You have found out the rate at which the function is changing. Or like you found a formula, depending on what x is, like minus 180, is it minus 90, is it 0, is it 45, you know, whatever x is, your input is. You put it in here, get cos of it, and that will tell you the slope. So I'm after finding a formula for the slope of the curve. So here's my formula for the curve. You know, I inputted that into my calculator a few minutes ago, got up my table, graphed it, and then, you know, joined it all together if we're looking at x is any real number. And then went to my log tables. You know, I didn't have sine 5x or anything like that. I had sine x, which is perfect because that is exactly here on the left-hand side of the page. Look across the right-hand side of the page. Differentiation of it is cos x. I now have a formula for the slope of this curve. So let's try it. This is probably the easiest one to see. It looks like it's a 0 here, slope of 0 here, slope of 0 here, you know, like, so, you know, I was climbing up the hill. There's a point of where I'm perfectly level on the hill, and then I start to maybe roll down the hill or whatever, or, you know, skiing slopes, all that sort of stuff. You can have a look at that. So, and maybe just look here. We know what to expect here. We know that the slope is 0. It looks it anyway. But let's test it out. If I want the slope at x equals, so we're on the x-axis, at x equals minus 90, then I type in cos of minus 90, and I get 0. Which means the slope here is 0. Yeah, I was right. Now, if we look here, maybe at minus 45, I should get a plus answer. I don't know what it'll be. You know, I can't tell. I can just estimate it's going to be a plus. So let's do, so I want the slope. So I'm using my slope formula at x equals minus 45. Okay, I'm just going to change that to a decimal. So, okay, it's not a slope of 1. We knew it was going to be a plus, but it's almost, you know, maybe 0.707 of a slope. Maybe it might be a little bit steeper here. You know, if you think about it, any hill, there's a little bit of a climb maybe, and then it gets a bit steeper, and then it starts to get less steep, and then it levels off. So I'm wondering maybe if I type in the cos of 0, what would I get? Because I want to know the slope at x equals 0. And I get 1. So it's maybe about 0.7 here. And then by the time I get to here, it's a slope of 1. You know, let's type in the cos of 45. Oh yeah, so it's gone back to 0.7. That kind of makes sense. And then here, I'm sure I'm going to get 0. So the cos when x equals 90. Yeah, slope of 0. So that's what we're doing. You have your function. I, at the start here, would just be graphing my function just so I can see it. Then I go to my log tables. I'll get the differentiation of that function, and then I will check out, so I can get as much understanding as possible. What the hell does that even mean in this particular situation, in this particular graph? How does it work? And can I estimate the slope and then check what really is the slope? There's other functions, so I said I'd have a look at this one. You know, log and base. So log of x and the base e is what this is. It's the shortened version of it. And if you want to know what that function looks like, I threw it into my calculator. I went from -3 up to 5. All of these are errors, which again, if you kind of understand logs, it should make sense as to why I kept getting an error for each of those, any minus numbers and 0. And then I could start plotting over here, and this is the graph that I got. And again, it looks maybe like, looks like it's a plus all the time, actually, always going up. But it was quite steep at the start, and then maybe gets less steep as we go along. So, is this in my log tables? Yes, it is. What is the differentiation of it? In my log tables, it's just 1 over x. What have I just found out? That is a formula for the slope of that curve. So the slope isn't consistent, so no wonder I have a variable here. And let's test it out. What does that look like? Maybe definitely a positive slope, and it's probably going to be the steepest part of the curve. So when x equals 1, I'll have 1 over 1, which is 1. So when at the point x equals 1, that's a slope of 1. Now I'm estimating here, even just by my graph, my sketch here, that I'm probably just get less and less steep as we go along. So maybe that's the steepest my graph is at that point. But let's check it out. What happens when x equals 2? Well, I'd have 1 over 2, so a half. So out here, yeah, it's definitely starting to level off, not level off, but get less steep. What about at x equals 3? I'd have 1 over 3. So the slope here is a third, so it's getting, you know, less steep again. 1 over 5, and so on, depending on what part of the curve you're looking at.